In the vast expanse of the cosmos, the dance of particles forms the very fabric of our universe. From the smallest quantum particles to the largest celestial bodies, the universe is a symphony of complex interactions and energies. Each star, planet and galaxy is a testament to the intricate and interconnected nature of these fundamental entities. Our journey into understanding this complexity begins with the smallest building blocks of matter, elementary particles. To grasp the essence of our universe, one must delve into the microscopic world where particles like quarks and leptons reign supreme. These particles are not merely abstract concepts, they are the very essence of everything we see and touch. By unraveling their mysteries, we step closer to comprehending the origins and the mechanics of the universe itself. The exploration of these particles is not just a scientific endeavor, but a voyage into the heart of existence. Our understanding of these particles has evolved over the years, with each discovery bringing us closer to the ultimate truth. From the protons and neutrons within the atomic nucleus to the elusive Higgs boson, the story of elementary particles is a tale of curiosity, persistence and wonder. It is a story that continues to unfold, with each chapter revealing new layers of complexity and insight. As we embark on this exploration, we will dissect the fundamental components of matter, delve into the forces that govern their interactions, and speculate on the hypothetical particles that could redefine our understanding of the universe. Our journey begins at the very core of matter, where the building blocks of our reality reside. At the heart of every atom lies a nucleus, composed of protons and neutrons surrounded by a cloud of electrons. These are the elementary particles, the fundamental constituents of matter. Protons are positively charged, neutrons are neutral, and electrons carry a negative charge. Together, they form the atoms that make up everything in the universe. Protons and neutrons are not indivisible, they are made up of even smaller particles called quarks. These quarks are held together by the strong force, one of the four fundamental forces of nature. The strong force is mediated by particles known as gluons, which act as the glue holding the quarks together inside protons and neutrons. This binding ensures the stability of atomic nuclei. Electrons, on the other hand, belong to a different class of particles known as leptons. Unlike protons and neutrons, electrons are truly elementary. They are not made up of smaller particles. The stability and behavior of atoms depend heavily on the interactions between these electrons and the atomic nucleus. This delicate balance of forces and particles defines the structure and properties of matter. Understanding these elementary particles and their interactions is crucial for comprehending the physical world. Each particle plays a distinct role in the grand scheme of the universe, contributing to the diversity and complexity of matter. As we delve deeper, we will uncover the intricate details of these fundamental entities and their significance in shaping our reality. Quarks are the fundamental constituents of protons and neutrons, and they come in six distinct types, known as flavors. These flavors are up, down, charm, strange, top, and bottom. Each type of quark carries a specific charge, which contributes to the overall charge of the particles they form. Up quarks have a charge of plus 2/3, while down quarks carry a charge of minus 1/3. Protons consist of two up quarks and one down quark, resulting in a total charge of plus 1. Neutrons, on the other hand, are made up of one up quark and two down quarks, giving them a neutral charge. The charm and strange quarks are heavier than the up and down quarks and play roles in the formation of certain unstable particles. These particles, although not part of ordinary matter, are crucial in high-energy physics experiments and cosmic ray interactions. The top and bottom quarks are even heavier and are typically produced in high-energy collisions within particle accelerators. Their discovery has provided significant insights into the fundamental structure of matter. The interactions between quarks are governed by the strong force mediated by gluons. Gluons carry the color charge, a property analogous to electric charge but related to the strong force. Quarks exchange gluons, which creates the strong attraction that binds them together inside protons and neutrons. This phenomenon, known as color confinement, ensures that quarks are never found in isolation, but always within composite particles. The study of quarks and their interactions has been pivotal in advancing our understanding of particle physics. These tiny entities, with their diverse properties and behaviors, form the foundation of the Standard Model, which describes the fundamental particles and forces of the universe. As we further explore the nature of quarks, we unlock deeper truths about the very fabric of reality. Leptons are a family of elementary particles that includes electrons, muons, tau particles, and their corresponding neutrinos. Electrons are perhaps the most well-known leptons, as they are essential components of atoms and play a crucial role in chemical bonding and electricity. Electrons have a charge of -1 and a very small mass compared to protons and neutrons. Muons and tau particles are heavier counterparts of electrons. They have the same charge of -1 but significantly greater masses. Muons are about 200 times heavier than electrons, while tau particles are approximately 3,500 times heavier. These heavier leptons are unstable and decay into lighter particles, including electrons, within a fraction of a second. Despite their instability, muons and tau particles are important in high-energy physics experiments and cosmic ray interactions. Each of these charged leptons has a corresponding neutrino: the electron neutrino, muon neutrino, and tau neutrino. Neutrinos are neutral particles with extremely small masses and interact very weakly with matter. They are incredibly abundant in the universe and are produced in nuclear reactions, such as those occurring in the Sun and other stars. Neutrinos can pass through enormous amounts of matter without being absorbed, making them challenging to detect. Leptons, with their diverse properties and interactions, play a vital role in the dynamics of the universe. The study of leptons, particularly neutrinos, has led to significant discoveries, including the phenomenon of neutrino oscillation, where neutrinos change from one type to another as they travel. This discovery has profound implications for our understanding of particle physics and the universe as a whole. Section 5. Force carriers, mediators of fundamental interactions. In the realm of particle physics, forces are mediated by specific particles known as force carriers or gauge bosons. These particles are responsible for the fundamental interactions that govern the behavior of matter. There are four fundamental forces: electromagnetic, weak, strong, and gravitational, each mediated by a different type of force carrier. The electromagnetic force is mediated by photons. Photons are massless particles that travel at the speed of light and are responsible for electromagnetic radiation, including visible light, radio waves, and X-rays. This force governs the interactions between charged particles and is essential for the structure of atoms and the behavior of electromagnetic fields. The weak force, responsible for processes like radioactive decay, is mediated by the W and Z bosons. These particles are much heavier than photons, which accounts for the short range of the weak force. The W boson comes in two types, W plus and W, corresponding to positive and negative charges, while the Z boson is neutral. The weak force plays a crucial role in nuclear reactions and the synthesis of elements in stars. The strong force, which binds quarks together inside protons and neutrons, is mediated by gluons. Gluons are massless particles that carry the color charge and create the strong attraction between quarks. This force is the strongest of the four fundamental forces, but operates only at very short distances within atomic nuclei. The exchange of gluons between quarks ensures the stability of protons and neutrons. Gravitational force, the weakest but most pervasive of the fundamental forces, is hypothesized to be mediated by gravitons. Gravitons are yet to be discovered, but they are predicted to be massless particles that carry the force of gravity. The search for gravitons and the understanding of gravity at the quantum level remains one of the most significant challenges in modern physics. Section 6. The Higgs boson, the mass giver. The Higgs boson, often referred to as the God particle, is a fundamental particle associated with the Higgs field. This field permeates the entire universe and is responsible for giving mass to other elementary particles. The discovery of the Higgs boson in 2012 at the Large Hadron Collider, LHC, was a monumental achievement in particle physics and provided crucial confirmation of the Standard Model. Particles acquire mass through their interaction with the Higgs field. As particles move through this field, they experience resistance, similar to an object moving through a viscous fluid. This resistance is what we perceive as mass. The Higgs boson is the quantum manifestation of the Higgs field, and its interactions with other particles determine their masses. The existence of the Higgs boson was first proposed by physicist Peter Higgs and his colleagues in the 1960s. For decades it remained a theoretical entity, with no direct evidence of its presence. The construction of the LHC, the world's largest and most powerful particle accelerator, provided the necessary conditions to detect the Higgs boson. The confirmation of its existence was a triumph for the scientific community and a testament to human ingenuity and perseverance. The Higgs boson not only completes the standard model, but also opens new avenues for research. Understanding the properties of the Higgs boson and the Higgs field can provide insights into the early universe, the nature of mass, and the potential existence of new physics beyond the standard model. The study of the Higgs boson continues to be a vibrant and exciting area of research in particle physics. Section 7. Hypothetical Particles Unveiling New Horizons. Beyond the well-established particles of the Standard Model, there exists a realm of hypothetical particles that could revolutionize our understanding of the universe. These particles, while not yet observed, are predicted by various theoretical frameworks and could help answer some of the most profound questions in physics. One such particle is the graviton, the proposed mediator of the gravitational force. While gravity is well described by Einstein's theory of general relativity, a quantum theory of gravity remains elusive. The discovery of the graviton would bridge this gap and provide a unified framework for all fundamental forces. Similarly, axions are hypothetical particles that could explain the nature of dark matter, the mysterious substance that makes up most of the universe's mass. Supersymmetry, a theoretical framework extending the Standard Model, predicts the existence of sparticles, or superpartners to the known particles. These include quarks, leptons, and neutralinos, among others. The discovery of sparticles would provide evidence for supersymmetry and offer solutions to several unresolved issues in particle physics, such as the hierarchy problem and the nature of dark matter. Other intriguing hypothetical particles include magnetic monopolies, which would carry a single magnetic charge, and Majorana fermions, particles that are their own antiparticle. Sterile neutrinos, which do not interact with the weak force, could also provide insights into the nature of neutrino masses and dark matter. Kaluza-Klein particles, arising from theories involving extraspatial dimensions, and tachyons, hypothetical particles that travel faster than light, further expand the landscape of potential discoveries. The search for these hypothetical particles is driven by the desire to understand the fundamental nature of reality. Each discovery has the potential to reshape our understanding of the universe, providing new insights and opening up new questions. The exploration of these particles represents the frontier of modern physics, where the boundaries of knowledge are constantly being pushed. Section 8. Conclusion: the ongoing quest for knowledge. The exploration of elementary and hypothetical particles is a journey into the very essence of the universe. Each particle, from the well-known protons, neutrons and electrons to the elusive Higgs boson and the speculative gravitons and axions, plays a pivotal role in our understanding of the cosmos. The study of these particles is not merely an academic pursuit, but a quest to unravel the mysteries of existence itself. As we delve deeper into the world of particle physics, we uncover layers of complexity and beauty that challenge our perceptions and expand our horizons. The discoveries made in this field have profound implications, not only for our understanding of the universe, but for the advancement of technology and the betterment of humanity. From the development of new medical treatments to the creation of powerful technologies, the applications of particle physics are vast and far-reaching. The quest for knowledge is a never-ending journey, driven by curiosity and the desire to understand the world around us. Each discovery, each new particle brings us one step closer to a comprehensive understanding of the universe. It is a journey that requires collaboration, innovation and perseverance. And it is a journey that we are privileged to undertake. In conclusion, the exploration of elementary and hypothetical particles is a testament to the power of human curiosity and intellect. It is a journey that continues to inspire and challenge us, pushing the boundaries of what we know and what we can achieve. As we look to the future, we can be confident that the quest for knowledge will lead to new discoveries, new technologies, and a deeper understanding of the universe we inhabit.